Hi, this is Jim Corkins, and we are now in our 6th lecture in kinematics. All right, and we're going to now concentrate on acceleration represented in position versus time graph and velocity versus time graph. Mostly what it looks like in position versus time graphs. Okay. Now, we've done some exercises before, and I would like you to practice these two. We did them, I think, 3 lectures ago about what is acceleration. So we did this in that acceleration thing. I want you to try this out again. Here you're going to match these letters to these numbers. Okay? And again, what you're doing is constructing these two equations, whether the accelerations are positive or negative or 0, and the velocities are positive, negative, or 0. So try that out. We also did a ball rolling down a ramp to the right and then rolling up another ramp to the right and then turning around and going back the other way. I would like you to try this. This ball is going to roll to the left across A, roll down B, and roll up C, come to a stop, come back down C, up B, and across to the right across A. So you're supposed to do position, velocity, and acceleration. So try reviewing those. But for now, let's again just remind us that instantaneous velocity is the velocity at a specific point in time. Okay? It's a very specific point in time. So this is a fraction of a second. All right? And so on a position versus time graphs, those incremental slopes will represent the velocity at those times. Okay, so that's just why I'm trying to remind you of this. Now, we had talked last time about the equation, which is 1/2 at squared plus initial velocity delta t. Now, you were working with an equation that had the initial position on the same side as the final, which was delta x, which is the displacement. So that is the same equation right here. Okay, and we've been working with velocity versus time linear fits, and this is the linear fit for this graph. Now, let's take a look at this. So on a position, let's interpret the velocity versus time graph. It looks like the object starts out at 0 meters per second, and across 3 seconds, it's going to have a final velocity of positive 15 meters per second. Let me write that right here. Meters per second. And so if we use this equation right here, it starts off with a velocity of 0, and then across 3 seconds, I want to use black for that time. This is 3 seconds. So 3 seconds times positive 5 meters per second over a second, we're going to end up with a final velocity of positive 15 meters per second. So this linear fit does work on this equation right here. Now here's what this means. All right, suppose the object started off with initial position of 0. All right, now the initial velocity is the initial slope at this initial position. So right here, see this blue right here? That slope is 0 meters per second. It is level. And that slope is occurring at a position at xi equals 0. So the initial velocity is the slope at that initial position. Okay? And this acceleration vector, again, is adding to this initial velocity vector to create a new velocity vector at 1 second. All right? So let's figure out what the velocity will be after the first second. So in this equation right here, I'm going to move that guy out of the way. So in this equation right here, I'm going to plug in for this new at 1 second, I'm going to plug in, you got 5 meters per second for every second times 1 second. Okay, and so what we're going to have is a positive slope of positive 5 meters per second. Okay, I didn't have to do that. I know you could have just done 1 times 5, but so this slope right here of positive 5 meters per second is occurring right here. So this is a slope of positive 5 meters per second. And that's occurring at this position. I don't know what that position is, but we could figure it out, right? So to figure out that final position, what that position is after the first second, we're going to go, we're going to put in a 1 right here. So that's going to be 1 squared times 5 divided by 2. So that's going to be positive 2.5 meters per meters. And then we're going to go 1 second plus 0, which is 0. And then plus the initial position of 0. So if we put in 1 second here and 1 second here, this is like, let's call this v1. This is the velocity at 1 second. So that's v1. And 2.5, so this position is positive 2.5 meters, which is the position at 1 second. So, and I'm going to write that again over here, the slope of this line, v1, is positive 5 meters per second. Okay, well, it looks like it's only increasing by 5 for every second. So here's our new velocity, which is positive 5 meters per second, right there. Well, at 2 seconds, it's going to be at positive 10. So the v2 here, the slope is going to be positive 10 meters per second. And that is occurring, and this is kind of a coincidence, but that new position, well, x final is going to be equal to, so now we're going to plug in 2 here. So 2 squared is 4. 4 divided by 2 is 2. 2 times 5 is 10. And this is going to be 2 times 0, which is 0 plus 0. So that x, so this guy right here, so 10 is going to be its position for the second with a slope of positive 10 meters per second. At the third second, we know that occurs, that it has a slope of positive 15. So v3, which is the final velocity, is a positive 15 meters per second. And so its velocity at its displacement at that third second. And let me just realize I should probably do this. So I'll call that 1, I'll call that 2, and I'll call this 3. Yeah. So this is 1, this is 2, this is 3. And that's going to be, now we're going to plug in a 3 here. Okay, so 3 squared times, 3 squared times 5. So what is that? 9 times 5, 45. 45 divided by 2, what is that? Positive 22.5? I don't trust myself. I'm going to double check that. So 9 times 5 equals divided by 2. I should learn to trust myself. So this is going to be its final position after 3 seconds. So this is its last position, and that is occurring at the 3rd second. So what this equation is it's telling you, it's using that initial slope, and that is going to be, that initial slope occurs xi at the initial position. So the initial position was 0 and the slope was 0, so that's a starting one. But after 3 seconds, the final slope is going to be positive 15 meters per second, which is what this is saying. And then we just have to plug in 3 here, and that'll tell us what our final position is. Okay, so these two systems right here tell us a lot of information about an overall object's motion. Okay, now this line is y-intercepts. Basically, the velocities here become y-intercepts on a velocity versus time graphs. So the slopes here become y-intercepts here. So for my calculus students, on a position versus time graph, you take those slopes and you take the first derivative, which will tell you the instantaneous slopes there. But what it also does, it turns those slopes into y-intercepts. Okay. So identifying slope and which one is a steeper slope versus a more level slope, and how one is positive and one is negative, is going to be crucial to understanding a position versus time graph. So in order to do that, we want to do this next exercise. Okay, so in this next exercise, you have a position versus time graph, and this is a car driving, and it's driving here and it's curving here. So these are its positions over time. So you're supposed to identify positive positions and negative, so positive slopes and negative slopes at each one of these points. Okay, and identify which one of those velocities are positive and negative slopes here, A, B, C, D, and E, and then we're going to construct this graph. So just take a moment and transfer slopes as positive, negative, or 0 to these points right here. To these points right here, and then construct a graph of positive and negative slopes over the period of 2 seconds. And I'm assuming this occurs at 1 second and this occurs at 2 seconds. Okay, go ahead and try this out on your own, and pause the video now. Okay, coming back from this, let's identify the slopes at each one of these. So it looks like this slope, which I'm going to use blue, is very positive, right? So that would be something like a positive slope. So a very steep slope. Here, the tangent line to this is 0. So that slope is 0. Here, we have a negative slope, but it's not too steep. But in D, it becomes really steep. So I'm kind of just thinking in terms of tangent lines. So this slope is much more steep than that. And then finally, in E, that is a velocity of 0. So the position, so positions of 0 occur at A, B, and C. A velocity of 0 occurs at B and E. A velocity that is positive only occurs at A. And velocities that are negative are C and D. So if we plot this out, A is going to start us out with a very positive slope. And then B is going to be 0. And then C is going to be a negative slope. And then D is going to be a really negative slope. So I've got to put a D there. And then E is going to be back to 0 at 2. So this is going to look kind of interesting. So this velocity versus time graph is going to look like a constant acceleration from A through A through D, but then something occurs at D and now it has a positive acceleration. So there is a constant negative acceleration there and becomes a positive acceleration here. Okay, so identifying those slopes in a position versus time graph and how they become a velocity or a y-intercept in a velocity versus time graph is crucial to building this skill set in understanding a position versus time graph and accelerated motion. Okay? So with accelerated motion, if an object is speeding up while moving to the right, if it starts out with, let's go ahead and plot this. So let's say in here we could say that this guy's initial position is right there, which is 0 meters. And this slope right here at that point, which is the initial velocity, looks like it's 0. So this is actually a 0 velocity. And if you look later on, right here at some later time, it's going to have a positive x final. And this is going to be the slope at the x final. So here we have a slope of 0, and here we have a positive x final slope. Well, if you start out at 0 and have a positive velocity in the end, you're adding to that, so this is going to be a positive acceleration. So this acceleration is adding to this 0 to make that slope even more steep in the positive way. All right. Now, over here, so this is speeding up while moving to the right. The acceleration vector is to the right, and all the velocities are to the right. All right, at 0 seconds, here is the initial position, which it does have some positive xi, and this is its initial slope, which is a negative velocity. So that's the negative initial velocity. Now, later on, at some later time, its final position looks like it's equal to 0, and its slope is equal to 0. So I'm comparing the initial position and initial slope to the final position and final slope. And so if you have a negative velocity, but later on you've come to a stop, somebody had to be, so you're moving to the left, and something has to be pushing you to the right to bring you to a stop. So this is going to represent a positive acceleration as well. This is also a positive acceleration. Okay. So you have a negative velocity and a positive acceleration. So you're slowing down your velocity, you're moving to the left, slowing down, and then you come to a stop. Something had to be pushing you to the right. Over here, the initial position is right there. So xi equals 0. Your initial slope is very positive. So xi, so that's going to be a positive vi. Your final slope, your final position, is a positive final position. And your final slope is 0 at that final position. So that is v final equals 0. So you have a positive velocity, and then you come to a stop. So you're moving to the right, and eventually you come to a stop. That means something had to be pushing you to the left. Okay, so your acceleration is going to be negative. Okay, so you're moving to the right, something's pushing you to the left and slowing you down. So that's why your acceleration is negative. Incidentally, this is, I think we said our final position is 0, and our initial position is positive there, so that works. This initial position is 0, and the final position is positive. Okay, here we go. We start off with a positive final position. Positive initial position. Okay. So this is a positive initial position, and the slope at that initial position looks like it's 0. So this is 0. All right. And eventually your final position is equal to 0. It occurs right here. And that final slope is a negative final velocity. So this final position is 0. So you're not moving, and then in the end you are moving to the left. So this is also a negative acceleration. Okay, so you start off not moving, and then somebody begins pushing you to the left, and you're just speeding up as you're moving to the left. This is slowing down while moving to the right. This is slowing down while moving to the left. This is speeding up while moving to the right. Okay, so notice how I was comparing, putting a dot here where the initial position, well, at time 0, and wherever that is. So at time 0, the dot initial y-intercept is way up here. But on this problem, the y-intercept is 0. And then I made a tangent line to that, and that is our initial velocity. Okay. The velocity versus time graph for accelerated motion when speeding up, we've kind of been doing this, but we're just going to check it. So here you have an initial velocity that is positive. And I should probably put an I there. And your final velocity is much more positive. So the slope of this line is your acceleration. Okay, so if you start off like moving 1 meter per second later on, or moving positive 2 meters per second, well, that acceleration is positive. That means you've got a positive velocity, you're moving to the right, and you're speeding up as you're moving to the right. So this velocity versus time graph corresponds to this position versus time graph. Okay, now here it looks like you start off moving to the left very quickly. And then in the end, your final velocity is equal 0. The slope of that line is positive, so that acceleration is positive. So you start off moving to the left and you end up coming to 0. So you're moving to the left, but you're slowing down as you're moving to the left. And so that's why this is a positive acceleration and a negative velocity. Here, this line you could tell is a negative acceleration. The final velocity here is going to be equal to 0. The initial velocity is very positive. So this final velocity is 0. That acceleration is negative, and the initial velocity is positive. So I should have probably added a 0 there. Okay. Here, your initial velocity is 0. But your final velocity is negative. And that slope is negative. So this is an object speeding up as it's moving to the left. This is an object slowing down as it's moving to the right. This is an object slowing down while moving to the left. This is an object speeding up while moving to the right. Okay? So I want you, based on what you just learned, I want you to try this exercise. I want you to match letters to numbers. Which position versus time graphs match acceleration versus time graphs? Okay, so I want you to take a moment, and the way we just talked about position versus time graph and velocity versus time graph, I want you to reason through how to match up numbers to letters. Okay, pause the video now. Okay, let's try something. Okay, so let's start off with A. A starts off with an initial velocity that is 0, and it ends with a final velocity that is positive. And the slope of this line is acceleration is positive. So we're going to look for a graph where its starting position, its starting slope is 0. So this one has a starting slope that is 0. And this one has a starting slope of 0. But we're looking for later on, it then has a positive velocity, which is going to be a positive slope. So later on, here we go, if we put a dot here, that final velocity is positive. So A matches up with 1. So A is 1. Okay, let's try D. Actually, let's try B. So this B starts off with a positive initial velocity, and then in the end, its final velocity looks like it's going to be equal to 0. And the slope of this line is negative. So we want to look at something that has a starting positive initial velocity. Well, this one has a positive initial velocity that's positive, and we also have here that is a positive initial velocity. But we want later on where the velocity is 0. So final velocity equals 0. This final velocity is the same as the initial velocity. So it looks like that acceleration is making that positive velocity become, subtracting from it such that it becomes 0. So it looks like B is equal to 5. All right, let's start out with number 2. Let's start out with the position versus time graph. Right here, the slope at that point is the initial velocity of that's positive. Oh, that should be negative. So it's got a negative initial velocity to start, and then in the end, its final velocity is going to be equal to 0. So we're going to look for a graph where it starts out with a negative velocity and ends with a velocity of 0. So this starts off with a negative initial velocity, and then its final velocity is equal to 0. And the slope of that line is the acceleration is positive. So you have a negative, you add positive numbers to it, eventually it's going to be 0. So it looks like d is equal to 2. All right, let's do number 6. We start off not moving, and then later on our final velocity is negative. So we're looking for a graph where it starts with initial velocity that is 0, and then later on its final velocity is negative. So it looks like C is 6. Again, the slope of that line here is negative. So if we're not moving and then you start adding negative slopes to this, it's going to, which the acceleration does, you're going to end up with a very negative slope in the end. All right. E looks like we start with an initial velocity that is negative, and it looks like that slope doesn't change. So the initial velocity is equal to the final velocity. So they're both the same. So we're going to start off with an initial velocity that is negative. And the final velocity has to be the same slope, which is also negative. And since it's a straight line, that means the acceleration is 0. So E is equal to 4. F, we start off with a positive initial velocity. The slope is 0. So the positive initial velocity is going to be equal to the final velocity. So the initial velocity and final velocity are equal. That means our acceleration is 0. All right, which looks like this one. So those two slopes are the same. So that means F is equal to 3. I believe that's a quiz question too. So that's how to reason through using a velocity versus time graph to identify a position versus time graph, and using a position versus time graph to identify a velocity versus time graph. Okay? Right. So we're going to do a mesh of everything. What we're going to do is we're going to match these motion diagrams to the proper position versus time graphs. So which one of these motion diagrams matches which one of these position versus time graphs. And then you're going to identify the velocity as positive, negative, and the acceleration as positive, negative, or 0. So This is a really good exercise, and it's going to teach you how to match up position versus time graphs to motion diagrams, and from there construct equations with the proper positive and negative velocities and positive, negative, and zero accelerations. So try this out. Let's do one on our own. Let's do B. Okay. So B, you could start off with the position versus time graph, or since I want to know what B is, it's moving to the right with a positive initial velocity, and its final velocity, I'm going to just call that 0. Notice its initial position is 0. Let me make this a little bit more organized. So its initial position is 0, so xi equals 0. And since this line is large and pointed to the right, so we're going to say the slope at that initial position is going to be, it's going to have a positive initial velocity. And over here, its final position is going to be a positive final position. But if you notice, that line is very small, so I'll just call that final velocity to be equal to 0. So we're looking for something that starts out right at the origin. So we have this that starts out at the origin. We have this that starts out at the origin with a position of 0, initial position of 0, and we have this one. We're looking for something that has a large positive velocity. So this one has a positive initial velocity vector. And this one has a positive initial velocity vector. So xi equals 0, but you have a positive initial velocity vector. This is xi equals 0, and you have a positive initial velocity. Here you have xi equals 0, but the initial velocity looks like it's 0. Okay, so, and then later on, the final velocity or final position is positive, and the slope there is going to be 0. So it looks like number 3 matches B. All of those arrows are pointing to the right, so this is going to be a positive velocity. But since those arrows are getting smaller and smaller and smaller, that means they're slowing down, so that acceleration is negative. So in other words, we would have a negative acceleration right here, a positive initial velocity. Well, technically our initial velocity would be 0. So this would be 0, and this will be 0. But it's moving to the right, and it's slowing down. Actually, that initial velocity isn't 0. I'm so sorry. This is a positive initial velocity, right? And its final velocity is going to be 0. So it's moving to the right and slowing down. So try all of these on your own and try doing what I just did. So pause the video and try this now. Okay, well, moving on. Let's go ahead and let's do A. Or actually, hold on. Let's try doing number 1. Number 1 starts out with, it's got an initial position that is positive, so that'll be the positive 50. and the slope of that line is negative. And then later on, it's still got that same slope. Negative final slope is the same as the beginning slope. Its final position is 0. So we're looking for a constant velocity that is pointed to the left, starting out at positive 50. So this looks like right here. So it looks like number 1. So F is number 1. All those velocities are negative, and that acceleration is going to be 0. So it's going to have a 0 acceleration, and those velocities are negative. Cool. Cool, cool, cool. Let's try another one. Let's start out with A. So A starts out with the initial position is equal to 0, and the initial velocity is equal to 0. It's going to end further away, where its final position is that positive 50, right here, positive 50, and its final velocity is also positive. So we're looking for something starting out at 0 with a 0 slope, and then later on it's got that x final, which is positive. So this will be at positive 50, and that slope, v final, is going to be positive. I wonder why it's taking a little while. Let's try this. So this slope is positive. So it looks like A is matched to 4. All those velocity vectors are pointed to the right. And that acceleration, it starts out at 0, and something must be pushing it to the right to speed it up. So that's going to be a positive acceleration, which means this is positive and this is positive, as well as, well, it looks like our initial velocity is 0 and 0 here. Okay. All right, let's try number 2. Number 2 starts out at x final is positive, and that slope is 0. V final equals 0. So we're going to look for a vector that is 0, but starting out at positive 50. And then later on, our x final is going to be equal to 0, but our final velocity is going to be negative. So we're looking for something that is speeding up as it's moving to the left. If it starts at 0 and it has a negative velocity, that is going to be a negative acceleration. Incidentally, this is an acceleration of 0, straight line. This is a negative acceleration. This is a positive acceleration. All right, so we're looking for something starting out far away with a small velocity vector. So initial velocity is pretty much 0, but we have a positive initial position. And then in the end, it's got a final position that is equal to 0, but its final velocity is positive. Nope, that should be negative final velocity. Right there. So this is going to be something, so C is going to be 2. It's going to have a negative velocity. Well, it's going to acquire more negative velocities. and that is because it's being pushed to the left. So this is going to be negative, this is going to be negative, this is going to be negative, and this is going to be negative. Okay? Only 2 more to go. All right, D looks like it starts off with a positive initial position, but has a negative initial velocity. All right, so positive initial position, but negative velocity. So xi equals 0 is positive. But vi is negative. In the end, its final position is equal to 0, but its final velocity is also equal to 0. So in the end, its final velocity is equal to 0, and its final position is equal to 0. All right. So in other words, you're moving to the left, you have a negative velocity. This is D is number 5. And it's got to be pushed to the right to bring it to a stop. So this is going to be positive, and this is going to be positive. This will be negative, and this will be negative. And then ultimately our final velocity is going to be 0. And our final position will be, well, it'll be negative. All right. The final one is pretty easy. It's just got the same final velocity as the initial velocity. I'm going to say this is positive acceleration. This acceleration is going to be equal to 0 since it's a straight line. And the final position is also positive. So that looks like that is going to be, E is going to be 6. And that is going to be a positive velocity, but A is equal to 0. So in other words, you're going to have a positive velocity here, positive velocity here, but this doesn't exist. So the final velocity is the initial velocity. Okay. All right. Now we're going to do the same thing that we just did, and this is our last activity on this. But this is matching these position versus time graphs right here to the motion diagrams and doing the same thing we just did, but and constructing those equations here. So I want you to try this on your own, and we'll do it in a second, but try doing this all by yourself, okay? And pause the video now. Okay, so A looks like it starts off with a 0 velocity. And its final velocity is a positive final velocity. So we're looking for something that starts off with a 0 velocity and then has a, so VI is equal to 0. And the final velocity is a positive final velocity. And that acceleration, the slope of that line, is going to be positive. So it looks like A matches up with Roman numeral 5. And that's going to show a positive velocity and a positive acceleration. In the graph, though, the initial velocity is 0. But it has a positive velocity, a positive acceleration. Okay? All right. Let's start off with a velocity versus time graph. Let's do this one. This starts off with a negative initial velocity, and its final velocity is equal to 0. And the slope of that line is positive. So we're looking for something that is moving to the left, but is slowing down, slowing to a stop as it's moving to the left. So it's got to start with a large initial velocity vector. So a large initial velocity vector, and its final velocity is equal to 0. Okay? So D looks like it matches up with Roman numeral 2. And that's going to be a negative velocity and a positive acceleration, because the slope of that line is positive acceleration. So positive acceleration, negative velocity, and the final velocity is 0. All right. Let's try another one. Let's try this one. Let's start off with B. B has a positive initial velocity, and its final velocity is equal to 0. All right. So it's going to have a positive initial velocity, but the final velocity is going to be equal to 0. And so that's going to be a negative acceleration because the slope of that line is negative. So it looks like B matches up with Roman numeral 3, which is a positive velocity, a negative acceleration, and that final velocity is also 0. So negative acceleration, positive velocity, and final velocity is also 0 on this one. All right, let's do VI. VI starts off with an initial velocity that is equal to 0, a final velocity that is negative. I just kind of follow this line over here. And the slope of that line is negative. So this starts off with an initial velocity that is 0. The final velocity is pointed to the left. So it looks like C matches up with Roman numeral 6. Those velocities, for the most part, are going to be negative, although it starts off with a 0 initial velocity, and that acceleration is negative. So if we built those equations, that would look like this, and we know that final velocity would be negative. Okay. All right. These last two, really simple. We've done them before. E is going to be Roman numeral 4. So the initial velocity, the positive initial velocity, is going to be equal to the positive final velocity. And that acceleration is equal to 0. So this is going to be positive, but the acceleration is 0. So in other words, you're going to have a positive initial velocity here and here, but there's going to be no acceleration at all. Okay, last one. So last one is F. So we know F is going to be matched up with Roman numeral 1. It's moving to the left the whole time, and since those dots are equally spaced, that is telling us the velocity is constant. That means the initial velocity is equal to the final velocity, although that acceleration is equal to 0. So this acceleration, it doesn't exist, but we have a negative velocity. The final velocity is equal to the initial velocity. So this is matching up position versus time graph and velocity versus time graphs with motion diagrams to construct equations. And I hope you learned a lot. And I'm just going to make sure we're going right over to here. Ooh, quite a bit there. And so this was 1.6. Acceleration represented in position versus time graphs and velocity versus time graphs. Thank you.